Okay, good morning, everyone. I'm Shawn, and I'm going to talk to you about our equivariant filter design for stereo camera SLAM. First, I want to give a little bit motivation. So SLAM has been an active area for research for several decades. So traditional filter-based SLAM algorithms, particularly things like the extended Kalman filter, tend to perform poorly in such nonlinear systems. Most of them suffer from the issues related to the unobservability of the global reference frame. And the equivariant filter, EQF, is a general filter design for systems that admits Lie group symmetries on homogeneous spaces, which allows us to use the powerful Lie group properties. And by posing the filter directly on the SLAM manifold, we can effectively avoid the unobservability issues. Also, we chose stereo camera SLAM because it's cheap and the depth information is directly observable, which makes it a good choice for visual SLAM problems. So what have we done in this paper? We applied the equivariant filter design to the stereo camera SLAM problem by lifting the system dynamics onto the symmetry Lie group and linearizing the global error at the fixed origin. We show that the SLAM invariance leads to simplify the dynamics of the underlying Riccati equation. And finally, we propose an innovation lift method to lift the filter innovation from the SLAM manifold to the total space where the real system is defined. So first, let's talk about the system formulation. Let's say we have the total space with elements representing the robot pose and landmark positions in the global reference frame. Then the SLAM manifold is obtained by factoring out the reference frame. And the elements on the SLAM manifold are invariant to any rigid transformation of the reference frame. So that is our state space, a smooth manifold. And we also have an input space V, which is a vector space. Then we have a system function F, which for any vector V in the input space, it gives a vector field on the manifold. And of course, since we are designing an observer, we need a system output as well. So in this stereo camera case, we model the system as a robot with two rigidly attached cameras. The output is a measurement from the two cameras, and H is the output function. Capital Pi is a camera projection function, and T is a camera offset from the robot. Then let's talk about the system symmetry. So on the SLAM manifold, there exists the SLAM Lie group with a transitive right group action phi. So we lift the system dynamics to the SLAM Lie group using an equivariant lift. The lift is a map from the SLAM manifold and the input space to the Lie algebra of the group. And it needs to satisfy the lift condition, which tells us that the dynamics defined by lambda on a group project back down to the dynamics on the manifold. And this allows us to think about a lifted system. So we have a system on a Lie group with the dynamics as shown on the left. And the trajectory is entirely determined by the Lie group state X and a choice of the origin cosine 0 and the input signal U. Then because of the way we've constructed the lift, that trajectory projects back down to a valid system trajectory on the manifold. Okay, so that's what we use to define our observer dynamics. We begin by choosing some origin configuration cosine 0 in the state space. Then we use that to define the observer dynamics entirely on the group. We also choose a local coordinate chart and linearize the error dynamics using the chart. And it gives us these linearized dynamics of the global error. Now, this matrix A0T, which is the state matrix, so in a general EQF design, this matrix is entirely determined by the origin configuration cosine 0 and the origin velocity V0. However, in this particular SLAM case, since the lift function we choose is independent to the system state, so the proposed system kinematics is not only equivariant, but also invariant, which makes the state matrix A0T always 0. And this part is further explained in the paper. So if we want a filter for this system, we simply choose to apply a Riccati observer, and it gives these dynamics of the EQF. So we place the observer on the Lie group. In the first equation, our observer dynamics are entirely defined on the group. X hat, which is our observer state, is a group element. And what you see in here is first a first part involving lambda, which is just copying the SLAM manifold, which is just copying the dynamics on the SLAM manifold. Then there is a delta term, which is an innovation that we have got choose somehow. Then the second equation shows how we choose a Riccati observer innovation from the linearization of the global error. And at the bottom, we have the actual matrix Riccati equation for the gain matrix of the observer. And finally, the presented EQF is posed directly on the SLAM manifold, where there is no notion of a global reference frame. However, in practice, it's often required to describe the estimated robot pose and landmarks with respect to an inertial reference frame. So we've proposed a method to lift the innovation from the SLAM manifold to the total space by minimizing the motion of landmark points with respect to the current choice of inertial frame. And the landmarks are weighted using the EQF Riccati matrix sigma. To validate the performance of our filter design, we've run a few simulations. So it's a typical stereo camera SLAM problem, where we have a robot moving with a constant velocity, observing 5 stationary landmarks, and the measurements are obtained through 2 rigidly attached cameras with certain offsets. The simulation begins with a certain amount of error in initial conditions. So from the estimated trajectory plot and the Lyapunov function, clearly the estimated state converges to the true state. And then to demonstrate the effect of the innovation lift, we repeat the simulation with perfect initial conditions and inject processing and measurement noises in the system. Then we measure the error in robot pose. For the system without innovation lift, which means delta is always 0, the error keeps accumulating, while for the system with innovation lift, the drift is clearly reduced. Finally, in order to demonstrate the proposed system in a real-world setting, we implemented the observer on the York dataset machine hall 1. In the algorithm, we use a very simple vision front end. So image features are detected using Harris County detector and checked using optical flow. So we compared the error statistics with and without applying the filter to the system, as shown in the table. So the filter is able to reduce the absolute translation error by about 20%, and the rotation error is reduced by about 50%. And overall, 29 centimeter error also demonstrates some good real-world performance. So in summary, we show that in this stereo camera SLAM problem, with the way we formulate the system and design the filter, the dynamics of the underlying Riccati equation is simplified. So, and the innovation lift method that we proposed effectively improves the performance of the filter. And the potential of our filter is demonstrated through simulation experiments. And that concludes my presentation. I'd like to thank my co-authors, Peter and Rob. Thanks. Yep.
Thanks so much, Shawn.
Thank you.
Okay, so for everybody on Slack, this is paper 126. So if you add that channel, you'll be able to type in some questions. So a first question from me is relates to the stereo, the fact of using stereo cameras. Mm-hmm. Can you comment on that? Do they have to be calibrated? How does the calibration of those cameras and errors in those cameras, or the calibration sort of factor into this? I don't quite understand, how that works.
So in this case, we choose, we use some calibrated stereo camera. So we assume it is well calibrated with a non-baseline and parameters. Yeah.
So in your simulation, so you haven't done yet any kind of to see how the performance changes when you haven't, as the calibration is worse. What that means for the accuracy of this method.
Yeah, it's an interesting point. Yeah, I think we can do that, but we're not focusing on such uncalibrated cases.
No.
Yeah.
No. Yeah, I simply wondered how that calibration may affect accuracy later down the track. So that's
right.
More an implementation sort of issue, I guess.
Yeah.
That's right. Any other questions? Okay, so what's your next bit of work you're going to do here? Will you take it into real images?
Yeah. So this equivariant filter design it's a general design. It's it not necessarily need to be applied for such SLAM problem or stereo camera SLAM. So we currently has a upgraded version of this, which we use IMU as well.
Okay.
And it becomes a VIO algorithm. We're using an IMU and a monocular camera, and we reach some state-of-art performance on the dataset, which is really good. And also, we are planning to include some range measurements into the filter.
Okay.
Yeah. So the problem with this is we don't have a very convenient way to construct such symmetry on each system. So for every different system, we need to construct it manually. We need to find the symmetry group. Yeah.
Okay, very good. Thank you. Let's have a look. No, we have no other questions on the Slack, so I think we'll call that to close there.
Thank you, John.
Thank you so much, Shawn. Thanks again.